Something else I was going to do. Uh, I want to be covering celestial navigation, just like actual celestial navigation. We're going to go through there's a couple of decent like mainstream videos that show how celestial navigation actually uses a flat planar surface to work with. So I want to get into, and I want to get into the measurements, and I want to apply it to like distances and stuff. See if we could actually use it utility wise. I want to get in. I've done a couple of shows on it, but it usually gets strung out because it's kind of a process. If you use a sextant to do celestial navigation, there's several different processes you have to go through to get your fix. You know what I'm saying?
Yeah.
But I mean, I think it's kind of cool. I don't want to bore the pants off people. I'm gonna do this thing again. He's got three. What, we got Beetlejuice, Sirius, Capella, Arc. How do you pronounce that? Arcturus. I don't know how to say this. Do he
Something like that, maybe.
and Regulus? Yeah. Those are he's got 1, 2, 3, 4, 5, 6 stars. He's gonna get a fix that. That's a lot of star. So you can trilaterate, or if that's the proper way to say it, your fix. You have
Right.
more of a points to go to, but they don't even have measurements to these stars themselves. The physical measure, so you don't have a hypotenuse. So yeah.
Triangulation means you know the distances, but you don't know the direction or something like that. It's like weird.
Yeah.
Anyway.
Yeah. Well, you're missing one part of your triangle, basically, and that's what happens when you're doing celestial navigation. Yeah,
makes sense.
yeah. But I mean, if we could actually get a measurement to these actual locations, it would make it easier to find out where you are. I think there's got to be a way to find these things, but it's a mystery as it goes now.
In reality, how we find things is we go by something in our, like the star above your head if you're in the ocean, because you can't, there's nothing to look at the ground. But if you're over the ground, then you just look for a marker, right? You look for a landmark, and that's how you know you're in the right spot, right? So I mean, there is no like real way to be completely confirmed until you've actually stood on the address or wherever that you're actually looking for, right?
Yeah,
you have to actually physically find the marker, right?
Yeah, I get that, but we don't have a real marker, a physical marker. We have an apparent position of a star.
Yeah, you're lacking that. But
this is why they do the equal elevation markers. They do 3 of them usually. So you take a flat plane above you because not everything on Earth is smooth. You know what I'm saying? So you actually get a direct fix. So instead of having that, you use those equal elevation angles to where above you, where it would be. You draw a plane above the plane. It's pretty funny.
Yeah.
It works. And those measurements are flat. So you calculate it, then you figure out where your fix is by the stars, and you get a measurement. There you go.
And Chris.
Yeah. You don't need calculus for that, do you? No.
No, not really. I mean, that's
not at all. Matter of fact, most people that do ship work don't take calculus. The people who navigate the world don't use calculus at all, do they? No. Nah. Don't need it.
Then finally, we need to correct for refraction, or more precisely, the additional refractive correction. This is impacted by temperature and atmospheric pressure. It affects stars close to the horizon more than ones at a higher altitude. This morning it was 12 degrees C and 975 millibars when we took our readings. So
you're trying to get an actual location as opposed to the apparent location due to atmo or moisture in the air, all kinds of other things. Because on a clearer day, you probably wouldn't have to correct it at all.
We're going to read down column J. 2 of our stars were high, so they didn't have any additional refractive correction.
There you go.
Arcturus was a bit lower, so we need to read off his correction, and we find it as plus 0.1 minutes. To get the calculated altitudes, we need that precise time of every site that we logged when we took the sites. Again, I'm going to do this in a table.
So basically you're going back to where you were before to find out how far you went. That's all it is. Your previous calculations is what you did in the morning before you get your... Yeah, I know. Well, they're in motion, so not all of them, but some of these stars are. So, because that's why they time them. That's the only reason. You got to know where the star is to find your longitude position, latitude positions. And you're not going to be exactly on longitude and latitude. You'll have to figure out degrees away you are from that longitude and latitude. Celestial navigation, I mean, it's very important. If back in the day when they didn't have the so-called GPS systems that they have now, or beacons and stuff where you can ping off of to find where your longitude and latitude are, technology has made a lot of this. Yeah. But I mean, there's a lot of parts of the oceans where there isn't anywhere, or you can't get satellites. You know what I'm saying?
Well, yeah, surprisingly, even though you can see the sky from every direction, you think that you'd always get a signal, but it's not actually true.
No, I wonder why. That's weird. I don't know, strange. Them satellites. Yeah.
If the local hour angle is greater
they consider
than
each
180
latitude
degrees,
and longitude a degree, so they're working those as degrees off the stars. You follow what I'm saying, Ryan? Are you still with me?
Yeah,
Are you fell asleep yet? So that latitude is what you're trying to get to that degree.
I've always wondered how to use a sextant.
East or west of it. So that's the way the sun travels, east to west, so, or the stars for that matter. You know, like everything else in the sky. But there are fixed positions, and the more fixed positions you get, and I think that's what we're going to be discovering, that there's more fixed positions. So this is going to be easy to do if you're out at sea. Yeah. Anybody learn anything yet? Are you tired of this?
Okay. No, I'm not tired of it. It's interesting, and I know it's going to take a while to figure it out and understand it properly.
Yeah. Well, it's complicated. I think there's different plates in the sky that actually rotate at different rates. The way it looks like, the way this is actually looking. You know, like there's different sets of stars at different elevations.
Well, if you think about it, Roger, if the sky is like, let's just say it's a dome shape, or maybe it's flattish or curved somewhat at the top or whatever. Okay. So let's say that it is. Wouldn't that make more sense to you? Like that from different angles, depending on where you're at on the ground in the middle of this big circle, right? That it would appear that they do rotate differently compared to where you're at, but only because of the way the light changes angle and different kinds of anomalous things that happen with light, right? You know what I mean?
Like he missed 3 of those stars at the beginning, too. Remember? It was too cloudy to see them. Yeah.
Right.
That's going to happen a lot. Gotcha. So you'll have to guess where they are. So you can find out how far you are from that latitude. You're like at 5.5 miles from it, so you can know what distance it is. It really
makes sense to me now why geometry was even invented. It wasn't because people wanted to play pool better. It was because they wanted to find their way around the ocean without having to put a marker, right?
Yeah. But I mean, this is how the Portuguese didn't even have this when they were doing it. They were using rule of thumb and like lining up stars. That's all they were doing. But once you get that one fix in that position, you can play off of that and go any direction you need to go, and you just time yourself to the next longitude and latitude. It's pretty simple, actually. But you'll be off a little bit because of the how many stars you have lined up. Yeah. He didn't bring up any curvature, any Coriolis, or any other thing you have to even account for in finding your longitude and latitude, which they actually claim that that's what they gauge it off of to begin with. You know, Coriolis effect is based on what longitude and latitude you're on. Like, nah, not really. That was fun. Show me the 69 nautical miles that you have to have and a radius value in order to do celestial navigation. I didn't see any of that in celestial navigation at all. I didn't hear it said once. Not any of that. He got a fix. He did it perfect. And you can throw your globe coordinates, but they're all flat. I hate to tell you that. But anyways, if you just look into any Cartesian system, they're all done on a flat.
Well, you might hate it, but I love telling
that. Oh, okay. I'm gonna go through a couple more videos like that in the next couple of weeks, where I'm just gonna point out like what they say isn't, you know. Even with their own videos, they're not ever done on a curved surface. None of it. You can't. I was going to get back to the 60 nautical miles, like the radius from the North Pole, and how we actually did reckoning. They use 60 nautical miles to get like a circumference of the Earth, or the, you follow me? Not a ball, just a flat nautical mile across. 60 is the range they
Some I'm
use.
gonna have to learn about. Yeah, I don't really know much. Like when you talk about like the sextants and the theodolites, and then nautical miles versus whatever. What's the other miles?
Statute miles.
Statute.
Yeah, statute miles are Roman statute miles. They're
Yeah, it's
actually.
something that I'll be learning if you when you cover it. Like
No,
I don't know
I've
much
done.
about
I did
that.
it. I covered that like a year and a half ago. I did a whole series on circumnavigation. Basically, I can do. I'll do another one. Yeah.
If I ever go out to sea, I'm bringing you. 'Cause
Okay.
you'll be